So we have our next speaker, and I'd like to welcome on stage Neville Gretch. He is the security researcher at the University of Athens, and he'll be talking about aspect of the contract library. Welcome.
Hello. Hi, I'm Neville. Thank you for coming. Today I'm going to be showing you under the hood of Contract Library, which does thorough smart contract decompilation and security analysis. So, what are we up to? We are static code analysis experts. Static analysis is about techniques for creating tools that model all possible program behaviors. This also includes the unintended behaviors, including bugs and security vulnerabilities. In this talk, I'm going to be talking about GigaHorse, which is the underlying framework of Contract Library. It's an EVM decompiler. So from bytecode back to a source level representation, but it's also a framework for doing sophisticated security analysis tools with very little code. So Contract Library is a free service, right? So you can go contract-library.com while I'm speaking. I don't want to scare you, but most of our security analyses are specified declaratively in the language called Datalog. Now, I don't want to bore you about the details of Datalog. I can tell you that it's Prolog without constructors, but that's not interesting. You can think of it as SQL on steroids and growth. So it's like SQL with complex recursion. And all our decompiler and all our security analysis are written in this. So take a look at this rule over here. Here we're saying that a loop is bound in its number of iterations by some variable var. That's the first line. Okay? And in order to conclude that property, you need to conclude all the properties in the body of the loop, in the body of the rule. So the first line says that if we have an induction variable I, which is actually a loop counter, and there's an exit condition cond, and I flows to that exit condition together with some other variable, which is not an induction variable, then we can conclude with some measure of success that the loop is bound in terms of its number of iterations by that variable var. Okay? We have over 1,000 of these rules running Contract Library. So I'm going to give you a demo now. So here it is. In order to use Contract Library, all you need to do is deploy your smart contract on the Ethereum mainnet or any of these testnets. Right? Let's take a look at one of these contracts. So as you know, on Ethereum, when you deploy a contract, you don't necessarily need to upload sources. But if you want to, on contractlibrary.com, you get a decompiled representation of all the smart contracts. So we can see features. Let me sort by Ether to get something more interesting. So here, for instance, we get data structures inferred automatically based on the pointer arithmetic that we see in the bytecode. Here we have mappings. You can also get like the function names. Those things are lost in the bytecode. You also get things such as private functions. Now, at the bytecode level, there is no such thing as private functions, but we know as software engineers that, you know, decomposing programs is the way to go. So let's get back here. So some cool statistics about Contract Library. We analyze every smart contract that's ever been deployed on the Ethereum mainnet or on the testnets, that's over 10 million contracts, which is over 1 billion lines of decompiled code. After decompilation, it takes less than 20 minutes to analyze the entire mainnet with one security analysis. Okay, so for one security analysis, less than 20 minutes. But obviously, we have many of these. In fact, let me show you one of these. So if you go here, contract library, here's a list of security analyses that are publicly available. Of course, we have many more. So let's see. Bad randomness. Same thing. I'm going to sort by ether to get the most interesting ones. And I'm going to take the first one, which has sources. So let's look at the source code of this. OK. Well, here it says bad randomness in get random number. So let's look at the implementation of get random number here. OK. Let's increase font size. So here, the author is getting a random number by calculating the block hash of a passed block. Okay? Now, this is not really a random number, because as an attacker, you can write a smart contract which uses the same random number generator. And if the outcome is in the user's favor, then you buy the lottery ticket or whatever. So many of these vulnerabilities that you find on contract library are true positives. And that's important because developers don't want to be bothered with a lot of warnings which don't mean anything. So in terms of analysis and decompilation success, we have over 99% of the smart contracts which we scale to. And contract library has the best analysis fidelity when compared to existing systems which do security analysis. So here's one of the heuristics that we use in the decompilation. So this is a disassembly of some Ethereum bytecode. The Solidity compiler erases the private functions when outputting the bytecode. But however, we can reconstruct them. So if you look at the first line, that's how a function call is compiled to. So the return address is pushed to the stack, followed by the data, followed by the function address that is going to be called next. And then you jump. Effectively, that jump is a function call, right? So it jumps till the end here, okay? Now, this function then just pops the data, performs its computation, and then jumps to whatever is on the top of the stack. Now, the last thing that was pushed to the stack was this return address. And this will then, therefore, just jump to the return address. Effectively, that's a return instruction. So the decompiler needs to understand all this. It needs to figure out where these jump labels and return labels are pushed to and track them via interprocedural calls. This is just one of the heuristics that we use. Finally, I want to show you how easy it is to write client analysis, security analysis, using the GigaHorse framework. We already have quite a few security analyses implemented, including reentrancy, bad randomness, which I showed you. And this actually looks for just outcomes where the user can have a favorable outcome based on a random number. Denial of service of gas, underflows and overflows in ERC20 contracts, various kinds of taint analysis, but also high-level decompilation, which is the stuff you see on contract library. So here are some of the high-level concepts which you can use as part of a security analysis. So we have syntactic sugar, where you can use familiar concepts, such as these solidity assembly instructions. You can also see that there's an instruction called private, and this is not something which appears at the EVM bytecode. High-level control flow reconstruction to reconstruct the control flow, such as loops or if statements, and that's sometimes useful for security analysis. I can give you an example of this, like for denial of service attacks, it's useful to reconstruct loops. Customizable data flow analysis. So there's some concepts from the security domain, such as taint analysis and simple data flow analysis as well. And these could be intra-procedural, so apply to the entire contract. These are fully customizable. Moreover, we also reconstruct the data structures. Of course, these are erased at the EVM bytecode level, but a client analysis, a security analysis, in order to be precise, it must reconstruct these. Otherwise, it will give a lot of warnings which don't mean anything. Guarded code analysis, so what properties, what modifiers apply to which code. Gas consumption analysis, so things such as how much gas do I need to reach this block, this statement, for instance. And that was useful for doing analysis of the Constantinople reentrancy, for instance. So here's a simple data flow analysis. This is written in Datalog. Okay, so if you want to create a custom data flow analysis, you say new local flow analysis. You customize, if you want to, the transfer functions. So this says that when I see a mask instruction, the inputs from the arguments flow to the output. And I'm also saying here that this data flow analysis only applies to loops, code in structured loop. This is useful for tracking how loop counters flow within their own loop. So here's an example of a client analysis. So this is very much inspired by Thomas's Kolinko example for doing ERC20 underflows. So in the second and third lines there, I'm saying that I want to analyze functions that match that signature. So that's at the transfer and transfer from ERC20 tokens. Okay, and then I'm saying that an underflow applies if those conditions hold. But you can see there in red, for instance, there's data flow analysis being used there. And at the last line, there is also the use of a control dependency analysis, controls with. So these are very sophisticated concepts, but they are easily used within a security analysis. In fact, the entire thing fits on just one slide, right? So, in conclusion, contract library achieves very good results in terms of fidelity. I attribute that to high fidelity decompilation and the use of sophisticated analysis technology, the use of the declarative specifications in Datalog. We provide very powerful analysis libraries which can be used in pretty much every security analysis, which means that every security analysis will be as powerful as any other, right, if it uses these libraries. We have industry strength scaffolding, so this is not just a research project. In fact, we scale to the entire blockchain and on multiple testnets too. Thank you very much.